Breaking news! 3 strong earthquakes rocked the Philippines on April 8, 2017. Why did this happen? Why do earthquakes occur?
An earthquake is a vibration of Earth's surface that releases energy in the Earth's crust. They are usually largely spread, causing greater damage to the Earth's surface or crust. Earthquakes are caused by stress that builds over time as blocks of crust attempt to move but are held in place by friction along a fault. The Earth's crust is divided into large plates that continually move over, under, alongside, or apart from one another atop the partly molten outer layer of the Earth's core. When the pressure to move becomes stronger than the friction holding them together, adjoining blocks of crust can suddenly slip, rupturing the fault and creating an earthquake.
How do we know this?
Earth has 4 layers: the inner core, the outer core, the mantle, and the crust. The crust is divided into huge plates that float on the mantle, which are called the tectonic plates. Plate tectonics is the modern version of the continental drift that was theorized by the brilliant, interdisciplinary German scientist
Alfred Wegener.
In 1912, he proposed the hypothesis stating that the continents had once joined to form a single supercontinent, in which he proposed that the supercontinent, Pangaea, began to break apart 200 million years ago and form the present land masses.
Wegener proposed that the continents plowed through the ocean floors by the means of the Earth's spin, tidal forces, and the wobble of the Earth's axis. Wegener's mechanism for plate movement was that the tidal influence of the moon was strong enough to move the continents westward. He was incorrect with his hypothesis, though. Not many believed in his theory, because his ideas needed to be backed up with more support and proof that would convince the others. It also challenged scientists in geology, geophysics, geography, and paleontology.
Wegener had several evidence to support his theory on the continental drift. He theorized that because the continents look like they could fit together, much like puzzle pieces that have drifted apart, he noticed that when you put the continental pieces back together, other things started to fit. Also, he noticed that a lot of the fossilized life found in the rock record didn't fit in the climates that they were found in. It also explained why look-alike animals and plant fossils and similar rock formations are found on different continents. Thus, he concluded that the continents must drift around the Earth, occasionally colliding with one another. Glossopteris, for example, they are an extinct group of seed plants that arose during the Permian on the great southern continent of Gondwana. These plants went on to become a dominant part of the southern flora through the rest of the Permian.
Mesosaurus, another example, was an early aquatic relative of reptiles, found in fossils from the early Permian period in South Africa and South America. It lived in freshwater lakes and ponds. It measured about 1 meter or 3.3 feet long. Because it is unlikely that the Mesosaurus could have traversed broad stretches of saline open ocean, their geographic distribution provided paleontological evidence corroborating the hypothesis that the southern hemisphere were once joined. The distribution of Mesosaurus was thus found of the earliest proof of continental drift.
Arthur Holmes and Harry Hess were the 2 scientists that helped provide evidence for Wegener's theory. Holmes theorized that convection currents move through the mantle the same way air circulates through a room, and radically reshaped the Earth's surface in the process. He proposed that upward convection might lift or even rupture the crust. The lateral movement could propel the crust sideways. In 1962, Harry Hess published The History of Ocean Basins, in which he outlined a theory that could explain how the continents could actually drift. Hess discovered that the oceans were shallower in the middle and identified the presence of mid-ocean ridges raised above the surrounding generally flat seafloor by as 1.5 kilometers. Hess envisaged that oceans grew from the centers, with molten material oozing up from the Earth's mantle along the mid-ocean ridges. This created new seafloor, which then away from the ridge in both directions.
Slab pull and ridge push are both the mechanisms for seafloor spreading. Slab pull is thought to be the primary downward arm of the convective flow in the mantle. Ridge push causes oceanic lithosphere to slide down the sides of the oceanic ridge. Most models suggest that the hot plumes of rocks are the upward floating arms in the mantle's convection. The unequal distribution of heat within Earth causes the thermal convection in the mantle that ultimately drives the plate motion.
Holmes and Hess used paleomagnetism to help them find their evidence. Paleomagnetism is the study of the record of the Earth's magnetic fields in rocks, sediment, or archaeological materials. One of the strongest pieces of evidence for plate tectonics have been paleomagnetism. It can be used to match up land masses that are now separated from each other, but which must have been joined. One of the most remarkable successes of paleomagnetism has been in the study of seafloor spreading. Their evidence was that the thermal convection in Earth's mantle could cause continents to move, but they subjected that the continents didn't move but were carried by larger pieces of Earth's crust called tectonic plates. Vines and Matthews published an idea in 1963 in a Nature paper called Magnetic Anomalies over Oceanic Ridges. It became the first scientific test of seafloor spreading and a crucial development in the theory of plate tectonics. Vines and Matthews noticed there was a symmetrical pattern of magnetic stripes on either side of the mid-ocean ridges. In addition, when the basalts of the seafloor were dated, they were found to be the same age at similar distances away from the ridge on each side. This suggested that the ocean floor was created at mid-ocean ridges, then was split in half by later activity and pushed sideways.
Scientists generally agree that the convection occurring in the mantle is the basic driving force for the plate movement. During convection, warm, less dense material rises and cooler, denser material sinks. The motion of matter resulting from convection is called convective flow. The causes of plate motion are mantle convection, which is the pushing and pulling of plates, and mantle plume/hotspot formation. A mantle plume is a mass of hotter than normal mantle material that is a second toward the surface, where it may lead to igneous activity.
The plate tectonics show us hotspots in geological structures. Hotspots are a concentration of heat in the mantle capable of producing magma, which rises to the Earth's surface. Hotspots are important because their evidence supports that the plates move over the Earth's surface. Geological structures are usually the result of the power tectonic forces that occur within the Earth. These forces folds and breaks rocks, form deep faults, and build mountains. Folds are when Earth's crust is pushed up from its sides. Also, faults are when tension and compression associated with the plate movement is so great that blocks of rocks fracture or break apart.
A few more things plate tectonics show us are mountains, rift valleys, ocean trenches, and ocean ridges. Where exactly do plate tectonics occur in the Earth's crust?
It occurs in the rigid outermost shell of the planet, the lithosphere. The different names of the several plates throughout the world are the North American plate, the Eurasian plate, the Philippine plate, the Pacific plate, the Arabian plate, the Indian Australian plate, African plate, South American plate, Scotia plate, Antarctic plate, Nazca plate, Cocos plate, Caribbean plate, and Juan de Fuca plate. Since it is not possible to go back in time and see what climates were like, scientists use paleoclimatology. Paleoclimatology is a study of ancient climates prior to the widespread availability of instrumental records. Scientists use imprints created during past climate, known as proxies, to interpret the paleoclimates. Organisms such as diatoms, forams, and corals serve as useful climate proxies.
There are three different types of plate boundaries. First is a divergent boundary. It occurs when two plates move apart. Along with developed divergent plate boundaries, the seafloor is elevated, forming the oceanic ridges. Also, deep faulted structures are called rift valleys. They are found along the axis of some segments.
Next is the convergent plate boundary. It forms when two plates move together. There are three ways this can happen. First, the ocean to ocean. It's when two oceanic slabs converge, one descends beneath the other, called subduction. This causes volcanic activity similar to what occurs in an oceanic continental boundary. A surface feature in the seafloor produced by the descending plate during subduction is called a trench. A curved chain of volcanic islands located at a tectonic margin, typically with a deep ocean trench on the convex side, is called an island arc. Next, the ocean to continent. It's when the leading edge of a continental plate converges with an oceanic plate. The less dense continental plate remains floating. Volcanic arc forms in part by volcanic activity caused by the subduction of ocean. Lastly is the continent to continent. It's when an oceanic plate is subducted beneath continental lithosphere. A continental volcanic arc develops along the margin of a continent. However, the subduction eventually brings the two continents together. A mountain created primarily by compressional stresses, which create floods in the rocky layer, is called folded mountains.
Lastly is the transformed plate boundary. There are margins where two plates grind past each other without the production or destruction of lithosphere. Each plate contains a combination of these three types of boundaries. Although the total surface of Earth does not change, plates may shrink and grow in area. This shrinking or growing depends on the location of convergent and divergent boundaries. New plate boundaries can be created because of the changing in the focus acting on these rigid slabs. Why is the continental crust only 4 billion years old while the ocean floor is less than 200 million?
This startling data is explained by their spreading seafloor and plate tectonics concept. Oceanic crust is being formed continuously from intrusion of mantle materials at the oceanic rises, creating new, younger seafloor. As the plates move apart, the inflow of molten lava forms new basaltic seafloor. The other sides of the plate are shear fault zones of transcurrent and transform faulting. The older oceanic crust is drawn downward with the upper mantle as the lithosphere subducts in the deep ocean trench regions. This does not happen with the continental crust. Because of its lower density, it rides upwards. The continents are progressively built while the ocean floor is always in the process of being renewed and destroyed. It's 1 a.m.